Good evening, my dear lovely JEE warriors. This is your Capto, this is your Captain Shreyas, and we are on to our Roar series. Yes, roar like a lion, and we are already deep into the portion. Like literally, so many topics have been covered in the Roar series with concepts, with the PYQ model questions, with application questions, handwritten notes, assignments, DPPs, everything a part of your Roar series. And yes, this is a batch for all the JEE aspirants 2025-2026. And today's topic, EMI, electromagnetic induction, guys. One of the most important, most involving, intriguing chapter of 12th standard. You know, it's very interesting, this chapter. You will see why, and a lot of concepts involved as well. So this is your Captain Shreyas, teaching, training, nurturing, sending kids to the best colleges. This year it's your turn. So how are you guys? And hope you are all geared up for the next leg of preparation. It's post Diwali now. Hope you had your small little break, but I hope you have also gathered your energy back. And this was one of the most asked topic also. A lot of you were asking me to take this. Hi Talent, hi Nikhil, Warrior Pandu, Whistle Pudu, WP Square. Yes, all the Warrior Pandus, Whistle Pudu. Yes, we'll try to do that also. Hi Devi, welcome. Hi Jyoti. Good evening, my dear lovely warriors. It's time to begin with the class. Hi Sadia. Yep. So let's begin with the class. Alrighty. So let's start. Now I'll tell you what. This chapter starts with a basic, very, question which you can ask yourself. See, when you have a static charge and then you have a static magnet. So when I tell a magnet, meaning like this, North Pole, South Pole, this is some charge. This static charge around it creates electric field. This basically, what does it create? It creates electric field, correct. Whereas a bar magnet around it, which is at rest, obviously it creates magnetic field lines which are complete closed loops. This is something which we have seen even before this, right? So it creates nothing but magnetic field around it. It creates magnetic field around it, and we have seen this in the chapter of magnetism sources. Like a current carrying wire also creates a magnetic field and all of that. So then the next obvious question is, if you have dynamic charges. So when what do I mean by dynamic charges? It means you have a wire which carries current, then that wire which carries current, obviously around it produces magnetic field. It produces magnetic field around it. This was given by Biot-Savart's law or your Ampere's loop law, through which you could find this. Here, finding the electric field was either done through Coulomb's law or through Gauss's law in electrostatics. This again came through Gauss law of magnetism, which is integral B dot A is 0 always, and also this magnetic field you can find out using Biot-Savart's law and other things in magnetism. So the only missing part of the puzzle, static charges giving electric field, static magnets creating magnetic field, but the same charge moves. Current is the flow of charge. It produces magnetic field. The missing part of the puzzle, you can guess it and put it in the chat box. We are talking about dynamic magnets. Dynamic magnets. Dynamic means moving. So magnets under motion. So this is moving. This is moving. This is in motion. So when that happens, the natural conclusion, looking at this, what should it create? Yes, what should it create? Definitely don't skip this chapter, Motivational Loom. This is not something which you would want to skip, especially when you have time. Oh, no problem. Bottle money. If you're watching Pathfinder, it is also great only. Yeah, the natural thing that will happen is it will basically create electric field around it. Yes, you heard it right. It is just going to create electric field around it, and you will see there will be, there will be electric field lines around it. Exactly. Electric field around it. That's what is going to happen. Yep. So no, it's not going to be a new kind of field. It's just going to create electric field. So this and this, this and this. So static charge creates electric field. Moving magnet creates also electric field. Stationary magnet creates magnetic field. Moving charge creates, magnetic field. So you can see the interrelation of electricity, magnetism, charges, magnets, current carrying wires, and also electromagnetic circuits. So all these things are interrelated, and the last part of the puzzle is completed in this chapter. This you studied in electrostatics, field, potential, and Gauss law. This you studied in the next chapter, magnetic effects of current. Bar magnets you studied in magnetic properties and all of that. So this is the last chapter which completes your electromagnetism. Is that right? Everybody understood the main concept of the chapter? Yeah. Changing magnets, moving magnets, dynamic magnetic things create electricity. So for finding that out, we revise the term called as magnetic flux, which we have already defined before, but still let's, I would say, revise that. Magnetic flux, which is nothing but the flow of magnetic field, the flow of the magnetic field through a surface, That's what magnetic flux is. So there are two ways about it. One is when the field is constant and the surface is flat, then it is a very, very straightforward thing. So say for example, this is your surface which we are talking about, and this particular surface is pretty much flat, like you can see, pretty much flat as you can see, and let's say there is magnetic field which is passing through it, and let's say the magnetic field is like this in that particular region. Okay, so this is the magnetic field passing through it or cutting through it. Then we define this area vector, which is a vector which is perpendicular to the surface, which is basically perpendicular to the surface like this, normal. So this is nothing but your area vector, usually A, some people also use S. And then we say that the magnetic flux, the symbol is phi B. This is the magnetic flux, is nothing but the dot product. Yes, it is basically the dot product of the magnetic field with the area vector. But you don't want to write it in dot product form. So you take the magnitude of the magnetic field, multiply by the area's magnitude, and then multiply by the cos of the angle between these two things. So that will also give you magnetic flux. So theta is the angle between them. Because magnetic field is measured in Tesla, area is measured in basically meter square in SI units. The unit of magnetic flux becomes nothing but a Weber. A Weber is a Tesla into meter square. The short form of Weber is the WB. It is only used for magnetic flux. Do not use it for electric flux. We are going to need this. That's why I'm revising this particular concept. But the same thing, if you had a curved area, maybe like this of sorts. Okay. Like this. This is a curved area maybe. Okay, this is some curved area. In that case, you take small area vectors. Let's say you take a small area vector here, then an area vector here, then area vector here, then area vector here, then area vector here, then here, then here, like that. You keep taking different area vectors at different places like this. Okay, this is how it will go. And then at each of these places, there will be some magnetic field cutting through it at different places. Different amounts of magnetic field will be there, and different amounts of flux will also be there at different places, something like this. Okay, just showing some random things. So the total magnetic flux, the total magnetic flux for any kind of curved area, will be nothing but, now we'll have to do integration, obviously, because there will be many small magnetic flux. So integration of d phi, and d phi is the small flux through any small such area. So the magnetic flux through any such curved area is the integration of the magnetic field at any point dot producted with the small areas, which is basically dA. So each small yellow one is a small dA area vector. So each one of them is like a small area vector, and at that local position, what is the magnetic field? So that is how you calculate it. I hope this is absolutely clear. Why is the sine component not taken? The sine component is not taken because the cos component will cut through it. Just visualize this. It is going to pierce through this, the cos component, whereas sine component will go over or below it. It will not pierce through it. Flux is something which passes through a surface. So whatever field is there, the cos component will pass, the sine component will pass parallel to the surface. It will not pass through the surface. That's the reason why we don't take the sine component. Yeah, you can prepare for JEE in 2 months, Muruke Tvashwar, but maybe you cannot cover all the chapters, but all the high weighted chapters at least you should definitely be able to do. Okay. Now, having said this, it's very important to know, imagine there is a region of surface. Okay, this is some region of surface. This is a surface, and let's say there were magnetic field lines which were piercing it. There were magnetic field lines which were piercing it at some instant of time. After some time, what happened is either the surface area changed, or the field changed, or the orientation of the magnets around it changed. So maybe some new amount of flux because something has changed. Okay, this is afterwards. This is before, and this is after. So what happened is, in this process, is there was a change in the magnetic flux. There was a change in the magnetic flux passing through that particular surface. The moment there is any kind of change in the magnetic flux, the moment something happens, either the magnets move, the area changed, the orientation changed, something happened. The moment this happened, if you happen to keep a coil in that area, if you have a coil, meaning a conducting wire like thing, okay, forget a conducting wire. Even if you don't have anything, it really doesn't matter. What happens is, because of the change in flux, you will see across that particular area where you have changed the flux, magnetic flux, you will see that there will be electric field which is induced. Yes, you will see electric field which is created. So electric field is basically induced. Electric field is basically induced. Actually, I've shown the direction wrong. We'll see that the direction will be given by another law. 1 second, guys. Electric field is induced. This is very, very important. Electric field is induced, and these electric field lines are not just here, but even around it over here, outside of it also, you will see electric fields are basically going to be induced. Yes. Electric fields are going to be induced in that particular region. Now, very important thing to know that this electric field which is induced is not due to charges. This is the most important thing. There was no charge. See, a charge can create electric field, but here the funny part is there is no charge. Magnetic field, empty space is there. Somewhere you are moving the magnet. In this empty space, magnetic field is changing. Automatically electric field is being created. Just imagine this. Just imagine this for a moment, guys. I have a magnet. I have a magnet with me. I'm just standing here, nothing is there. I move this magnet, the field lines passing through this region is changing. Automatically electric field is created. It is crazy to think about. It feels like magic. If you ask me what is magic, this is magic. Something happening somewhere, something else being created somewhere else. So this is the magic being created. It's really interesting. And I can show that to you in some of the simulations out here. Let's start by seeing some of the nice simulations. I think it's a very, very interesting simulation over here. Look at this. This is a bar magnet. A bar magnet, around it creates magnetic field. And if you can see, I reduce the intensity of the magnet, I will see that the field becomes very weak. If I make the magnet strong, the field becomes very, very strong. This compass tells me what direction is the magnetic field pointing in that vicinity. Yes, you can also see inside also the field lines continue. Now, this is for a stationary magnet. Similarly, if you take the example of an electromagnet, this is, okay, 1 second, not this. Yeah, if you take the example of an electromagnet, current is flowing, you can see it will also create magnetic field around it. So this is moving charges creating, you can see moving charges also creating magnetic field around that particular region. Now what we will do, observe this carefully. Stationary magnets, magnetic field. Moving charges, magnetic field. But look at this now. There is a coil, this bulb is off, no current, nothing is there, no battery is there. This is power magnet over here, it's doing nothing. But the moment I move the magnet here, do you see the bulb glowing? And this is exactly what Faraday saw 100 plus years back. And he was shocked to see why the hell did the bulb glow. He saw this moving magnet is suddenly lighting up the bulb. There is no battery, there is no cell, there is no engine, nothing. Still the bulb started glowing. Now if you think about it, look at the magnetic field lines. I don't know whether you are able to see it, but maybe I'll just darken this room so that you can see it now. Do you see the field through the coil? The field through the coil is changing. The flux is changing through the coil. Can you see that? As I move that magnet, you can see the flux, the field through that area is definitely changing. So because of that, what is happening, my dear students? Because the flux is changing, what did I just tell you over here? When the flux changes, it creates electric field, and it is not due to any charge, rather it is due to changing field. If there is electric field, what will that electric field say to the charges? What will the electric field do or say to the charges? Hey, I am field. Hey, you are a charge. I will apply force QE. I will apply a force Q into E. Q is the charge, E is the field, F is the force. So once force is applied on the charges, what will they do? They will start moving. And once the charges start moving, what does it create? Current. So is this current created through a battery? No. But this current was created by induced electric field. Electric field which was not generated by charge, but it was induced. Yes, this feeling came. That is called induced. So that's why the current is called induced current. There is induced current in it, and there will be a voltage which will be developed in that coil. There will be a voltage which will be developed in that coil. That voltage developed is then called induced voltage or induced EMF. It is called induced voltage or induced EMF due to these moving magnets. Funny part is, you need not have to move the magnet. You can even move the coil, still the bulb will glow. Just that somehow through the coil, you have to ensure that the flux will change. Somehow you have to ensure that the flux will change within the coil. You will see that the bulb is glowing. Do you see that? Yes. So changing magnetic flux creates induced electric field, which then forces the charges to move, which then creates induced current, and there is a terminal voltage in that coil which is called as the induced EMF or the induced voltage. Is this concept clear of EMI? This is what is there in EMI. Good evening, spread right. Got it? Ashwin, I would recommend you to use the crash books as well. Even if the wire was kept in a straight, even if the wire was straight, still the current would be produced. The current might be more or less depending on how much flux was changing. Yeah, so current can be produced not necessarily because it was a coil. Maybe it was some weird looking thing, but it should be a closed loop. Obviously, you can't say just one straight wire. It has to be complete. The circuit has to be complete. If the circuit is not complete, where will the electrons go? There will be no place to go. Got it, my dear warriors? Understood? So this electric field is induced not due to charges, but due to change in the magnetic flux. And I would say in the next slide, this then, if you have a coil, if you have basically a coil, you will see that there will be a current which is induced. So the induced electric field applies electric force on whom? The free charges on the conductor, on the free charges of the conducting coil, thereby what happens is electricity conducts, electricity is induced, and in the sense there is current which is induced in that coil, and also there is EMF which is induced in the particular coil. EMF which is induced in that particular coil. If that coil was not there, will there be current? No. Will there be EMF? No. Will there be EMF? No, because there will be no coil to measure that. But yes, there will be voltage difference, I can say, because the electric field is going to be there. So voltage difference will be there, but there will be nobody to force those charges as such to, conduct the electricity. So the coil is just enabling the charges to flow and helping us measure, the EMFs and I would say the current. But otherwise, there is always that electric field looking out for charges to be forced into motion and thereby creating and generating that electricity. Another interesting thing to note about this electric field is that, do you see the electric field lines are closed loops? How many of you notice this? Even when I have drawn over here, I never showed it starting from a point and ending somewhere else. Static charges are producing these kind of fields. They are never closed loops. Yes, magnetic field lines are always closed loops. But for the very first time, you are seeing electric field lines which are starting and ending at the same point. And you know why this happened? You know why this happened? Because they were not created only by charge. If there was a charge, electric field line should start if it is positive. If it is negative, it should end on it. But when there is no charge, where will it start from? Where will it end on? There is no place to start to begin with, no place to terminate on. Hence, they are closed loops. They are closed loops. Unlike due to static charges. Unlike due to static charges, they are basically closed loops, correct? And best part, I'll tell you, imagine you go around one such electric field which is a closed loop. You take a charge around that electric field line, along that closed path. Every time there will be work done, net work done will not be zero. So you will see that the total work done by that electric force along that closed path will not be zero. This is very important. That means it is not conservative in nature. It is not conservative force or conservative field, unlike due to static charges. Whenever you had stationary charges, yes, the field was conservative, but this field, which is created by induced nature due to magnetic flux changing, that is non-conservative in nature. Is this clear? So the very different kind of electric field. Yes, I hope this is absolutely clear. Logo, everything, every person has a different mindset, so that's the reason for that. So it's nothing like why is it 3 months, why is it 5 months? I mean, it depends. Like if you are getting more time, more obviously facilities, obviously the pricing will be different. If it is for a lot of students who want to make sure that they want to crack it in the first go, so we wanted to bring in an affordable crash course for all those students. Yeah. Yes. Is because the work was done in changing the flux? You can say that. You can say that actually. That's the reason why that electric field has not done zero work. You can vaguely say that. You will see that relationship when we discuss eddy currents. Okay. So now having said all of this, okay, now we are interested in, okay, sir, can you now quickly think and tell me what is the amount of electricity being created? So here is the logic. If you have a surface, if you have some surface and there was magnetic field over here which changed. So then I can say directly a change in the magnetic flux through a surface, or it's understood magnetic flux is always through a surface, causes induced electric field, which in turn can induce EMF and current in a coil. This EMF which is induced, magnitude wise, was found out to be the derivative of the change of the magnetic flux. Was found out to be the derivative of the magnetic flux with respect to time. This particular statement, what you are seeing over here, is precisely what is called as the Faraday's law. Is called as the Faraday's law. So Faraday's law tells me how much EMF is generated inside a particular coil due to changing magnetic field, and you will see that over here the magnetic flux can change due to one of the three reasons. So the flux can change due to one of these following reasons. Number one, the magnetic field changes. Number two is the area changes, is basically the area changes. Okay, this is the second possibility. And the third possibility is the orientation or basically the angle between the field and area will change. Any of these three things, you will see that flux will change, and because the flux will change, it will create the EMF. Who was Faraday? I mean, he was a scientist and he conducted experiments to figure out how to generate electricity through magnets. He spent months doing experiments, and accidentally one day, because of his apprentice, because of a person whom he had kept to assist him, he was able to figure out that okay, accidentally when he moved the magnet, he was able to see there was a fluctuation in the voltmeter readings, and that's when he discovered that okay, yes, this is what creates this particular electricity. If you ask me what is the value of the induced current inside that particular coil, that coil will be there over here. So if you ask me what is the value of the current which is induced in that coil, it will be nothing but how much ever induced EMF is there upon the resistance of that particular coil. That is what the induced current will be. You can also do one thing, induced current, you can also write it as how much ever charge will flow upon that particular time, and over here, this induced EMF, I can write it as how much ever flux has changed upon the time which it took to change that particular flux. You will see that the time will get cancelled on both the places, and you will be left with the amount of charge which flows inside that particular coil will be nothing but how much ever the flux changed inside the coil upon the resistance of that particular coil. This is also another formula which can be useful at times. And current is voltage by resistance is nothing but like your Ohm's law at the end of the day. This is like your Ohm's law. You can say that. Current is voltage by resistance. Current is charge by time. EMF is change of flux divided by time. Time cancels. So the charge which flows is change in the magnetic flux by the resistance of the coil. That is also something which you can see. Okay, so this is the main things which you should know about Faraday's law. I hope this is clear. Yep. All right. Logo, it is not about just teaching, it's about those additional things where you have doubt solving, you get the crash material, you get DPPs, you get crash oriented approach, you get a disciplined approach in the class doubt solving. Apart from that, you get tests, weekly tests, full syllabus, part syllabus tests, all India ranking, report card, right? You also have mentorship in the crash. If you take Crash Pro Plus, you have a dedicated student academic mentor. Apart from that, if you are the Crash Pro, you also get 24/7 doubt solving. So all these things, that discipline, that habit which builds up is what people look for. Otherwise, I can also become a doctor watching YouTube classes, but I'm not becoming a doctor by watching YouTube classes because maybe I'm not having that, kind of mentorship, or maybe I don't have that inclination. But even if I wanted to, I wouldn't do that, right? I would definitely enroll myself in, let's say, a college, and then, ensure that I get proper exposure, right? That's how it is. Haroon, I took your name, man. Yeah. Yes, you are going to have full syllabus tests in the crash course also. Yep. If area is doubled, yes, the flux will change. Any of the things, area has been changed. Area has been doubled by increasing the turns. Magnetic field changes. Orientation angle changes. Anything will cause the flux to change. Now, having said this, let's also see the next part of this law, which is also called as Lenz's law. Which is also called as Lenz's law. This Lenz's law tells me in which direction is this current going to be induced. This Lenz's law is going to tell me the direction of the induced current, and this direction of the induced current is such that it always opposes the change in the flux, the change in the magnetic flux. And why it does that is due to, the reason for this is due to law of conservation of energy. Just that. So if for some reason I will see that there is a surface, and there are two possibilities now. I'll just show it over here. Imagine there is a surface and there are two possibilities over here. And let's say this is that coil, and the surface has been marked. Earlier, there was maybe this much amount of magnetic field. This was before. Afterwards, what happened is the amount of magnetic field increased. Here, the magnetic field has basically reduced. So clearly, in this case, the flux reduced in this particular case, in this particular scenario, whereas in this particular scenario, the flux has increased. The flux has basically increased. What did I say? Any kind of current which is induced will always try to oppose that change in the flux. Observe now carefully. Here the flux has reduced. So to oppose it, it will try to increase the flux. So the induced current will now strengthen. It will now strengthen this particular flux. Whereas here, because it is increasing, it will now try to weaken that flux. It will now try to weaken this particular flux. That's the major difference. It's like you want to go out with your friends and you ask your parents that, okay, can I go out to play, and I want to have some fun, I want to enjoy with my friends, whatever. Parents tell you, no, you can't go. Then you're like, okay. Then one day you say, I want to sit at home, I want to go out with my friends. The parents are like, no, you have to go out, go play with your friends. So whatever you do, you get an opposition. You try to become less, they will try to strengthen. If you try to become strong, they will try to weaken. So that is what Lenz's law is. And this is based on conservation of energy. Just think about it otherwise. Imagine this law were not to hold true. That means if the flux tries to reduce, it tries to make it more weak. Or if it tries to become strong, it makes it even more stronger. Just imagine if that would happen. Imagine magnetic flux is increasing and it tries to increase it more. Where is that energy coming from? Who is giving that energy? And if it is trying to reduce and it is going to become even more weak, where is that energy going? So there has to be some compensation. So if one is trying to increase, it will try to weaken it. And if it is trying to become strong, this will try to again do the opposite. I hope this is clear. Yes. So what do I mean by strengthen it? I mean, imagine if the current has to go, if it can go like this or it can go like this. But if it goes like this, the thumb goes opposite, it will oppose this. I want to strengthen it. That means the induced field should be such that the current will be in the anti-clockwise direction over here. This is the direction of the induced current, because that current's field, magnetic field, this is induced field, will strengthen it. It will strengthen it. Whereas here, to weaken it, my thumb should come down. So my current will go like this. This is the direction of my induced current. So the induced magnetic field will try to weaken it. It is opposing it. I hope now it is absolutely clear how Lenz's law works. Is that clear? Everyone? Understood? Perfecto? Can we go ahead? Yes, got it. All right. Now, also very important that what happens is our Faraday's and Lenz's law together is usually written down like this. Faraday and Lenz's law combined together is usually written down like this, that the induced EMF is nothing but negative derivative of the magnetic flux. Negative derivative of the magnetic flux. This minus sign has come because of Lenz law. This is because of the Lenz law. And this thing over here has come due to Faraday. The magnitude is given by Faraday. The sign of it is due to Lenz. That minus sign signifies you are just trying to oppose that whatever change is there. That is what this is. Okay. I hope this is absolutely clear what Lenz's law is, what the induced EMF is, what the induced current is, and we can see that in action over here. Let's make the number of loops 1. Let's make the number of loops 1 and let's have a voltmeter and let's keep the area to be very small. Let's see how much the voltmeter deflects. Okay, it is deflecting so much. I'm moving it like this. If I move it fast, you will see it deflects more. Why? Because the rate derivative will be higher. If I move it slowly, then you can see the deflection is not much. But if the rate of change of the magnetic flux is fast, then you can see even more electricity and current is induced. So it follows our Faraday's law. What if I increase the loop's area? What if I increase the loop's area? And you can see when I increase the loop's area, then more flux will pass, so there will be more change. So you will see there will be more electricity, which is shown by this voltmeter over here. Yes, definitely. As compared to less area. Look at this, very little area over here. So I'm moving it with the same speed over here. It is giving me this much electricity. But the moment I increase this particular area and now I move it, it will definitely give me more amount of electricity. What will happen if I have more number of turns, like 2 turns? Then also you will see the electricity induced is even higher. And if I increase more turns, 4 turns, 5 turns, you can see the voltmeter is giving me even more reading, because the flux will cut it many times. So the change in the flux will also be increased proportional to the number of turns. Every time there is a turn, the flux in each turn will change. So that will create more electricity. So less turns, less electricity, whereas more number of turns, you can see more electricity. You can see that. Okay. And same thing, if the magnet is very weak, you will not see so much of electricity. You can see hardly it is moving because the magnet is very weak. Whereas if I take a strong magnet, now it starts moving. So the magnetic field matters, the speed of the magnets matter, relative motion should be there actually. Doesn't matter whether the magnet is moving or the coil is moving. Either ways, it will have the same effect. And area matters, turns matter. And if I move both of them together, then there is no relative motion, then there is no electricity which is created. As you can see over here, there is no relative motion, so nothing will happen. But the moment there is relative motion, you can see the coils will generate electricity and the voltmeter is showing some reading. But if it is same speed, then there is no deflection at all. Is this now into your head? What is EMI, electromagnetic induction? That's how the way physics is, Nikhil. I mean, yeah. Hi Jishnu, welcome. Badrinath, welcome. Hi Sanjay. Okay, I hope the simulation has made things absolutely very clear. Okay, so with this, I think it's good time now to start solving some questions on this. And let's start with some basic questions over here. I will show some situations the magnets will be moving in some or the other direction, and you have to predict which direction The question is, find the direction of induced current. Direction of induced current. That's all you need to figure out in all these examples. Okay, so let's try it one by one. You will get the answer. Just see whether the flux is increasing or decreasing. That's all, and see in which direction it is increasing or decreasing. This bar magnet is going to produce magnetic flux like this. It will create magnetic field lines like this, and it will cut through it here. It will cut through it here. Is that right? And this flux definitely is increasing. Because as the magnet comes close, all those field lines which were missing that coil will now be able to cut through it. So those field lines which were not able to go through it will now be able to cut through the coil, so more flux will pass. Whereas when you take it away, just imagine these were the field lines. Okay, as you take it away, you will see that as this goes away, these field lines will no longer cut. So definitely over here, the flux is reducing. Understood? First try to see whether it increases or it decreases. Okay. So if the flux is increasing here, according to Lenz's law, you should try to oppose that change. So to oppose it, the flux is coming down, so you will oppose it like this. So the induced field should oppose it. It will try to weaken it. Here the flux is reducing, you will try to strengthen it. So the induced magnetic field should try to strengthen it. Okay, if it is like that, weaken the field by inducing the magnetic field up. Hold your thumb up, the fingers turn like this. So the induced current will be in this direction. This is the direction of the induced current. Here the induced magnetic field is down. Hold your thumb down, the fingers curl like this. So the induced current will be in this particular direction. Induced current will be in this particular direction. So here it was anti-clockwise, here it was clockwise. Same logic you can apply it over here and see what happens. Observe it carefully. The south pole is coming closer. That means the magnetic field lines will be coming like this, like this, like this, even like this. And you will see that as it comes close, even those field lines which are out will now pass through the coil. So the flux definitely is increasing in this particular case. Is definitely increasing in this particular case. Whereas over here, as you can see, as it goes far and far away, as it goes far and far away, those field lines which are here will now move from outside the coil, So definitely flux is decreasing in nature. Flux is decreasing in nature, whereas here the flux is increasing in nature. So whenever the flux is increasing, you are going to create an induced field to weaken it. So how are you going to weaken it? By creating opposite direction. So the induced field should weaken it. The flux is going left, you weaken it by right side. Here the flux is decreasing, you strengthen it. So the induced field is going to give it strength. It is going to strengthen it. Okay. Hold your thumb like this in the direction of induced field. See how the fingers are coming. Curled fingers are coming like this. So this is the direction of the induced current. Whereas over here, hold the thumb like this, the fingers go like that. So this is the direction of the induced current. This is how you apply Lenz's law to get the directions. Is this absolutely clear? NTA has not given any update. All the other updates which random channels are doing, they are all unofficial. That's why I went live and told, please don't break your head. If something was important, urgent, I would have gone live. Or else it's not like just because it was holiday, Shreyas sir didn't make video. I really don't understand why you guys get worried about random updates. If it is official, no, Shreyas sir will come. If it is not official, it's chumma time pass, and that too for 2026 and 2027, which may happen, which may not happen. Why do you want to take tension about it? So for 2025, there is no change, guys. So don't break your head. Okay? Yeah. But yeah, the competition will be higher. That's something which I told you even before. Okay, let's do another example based on Lenz's law and see whether you guys can figure this out. Imagine it was given to you that there was a square loop and suddenly that square loop has been converted into a circle. So earlier, let's say there was magnetic field like this. Okay, this is your magnetic field. So can you figure out the direction of the induced current? What will it be? What will be the direction of the induced current in this scenario? A square loop has been converted into a circular loop. Come on, think about it. What will you do? First thing you will think, magnetic field didn't change, orientation didn't change, area changed. See, the perimeter of both the figures is the same because it's the same wire, because it's the same length of that particular wire. So what changed is the area. The area has basically changed. And if you ask me whose area is more for a given perimeter, the answer should be, yep, the area of a circle is always more than the area of the quadrilateral. Circle has always the highest area for a given perimeter. Correct. The more sided polygon it is, the more the area is for a given perimeter. Lesser the sides, lesser the area is for the given perimeter. Which means, if you ask me how much flux passed through, this part, versus how much flux passed through this part. Who will be having more flux? Obviously, the flux through the circle is more than the flux through the quadrilateral. So definitely from here to here, the flux has increased. If the flux has increased, the induced field should try to weaken it. The induced field should try to weaken it. Where is the magnetic flux going? Inside the plane of the board because of this cross. Cross means going away from you. Dot means coming towards you. So the flux is increasing inside. So the induced field should be towards you. The induced magnetic field should be towards you. Take the fingers of your right hand. Hold the thumb in the direction of the induced field. See how the fingers bend. That's it. So that is basically the direction of the induced current. It is anti-clockwise. It is anti-clockwise. Anil, even if you get 100 percentile but you are not 75% in boards, you will not be allowed for the counseling of NITs, IITs. So 75% is a mandatory criteria, okay, for admission for the general category. So keep that in mind. Okay, let's do another question, my dear warriors, coming up on your screen, and here it is. And here it is. Imagine there is a wire which carries some current, and then there is a square loop over here or some rectangular loop over here, and it is given that the current over here is increasing, is basically increasing. What effect will it have over here? So in this loop, what will be the direction of the induced current? What will be the direction of the induced current in this particular loop? That is the question. Let's try to solve this. It's also very interesting again. First of all, realize the current in this wire is increasing. This is not connected only to anything, it is just beside it in the same plane. What will happen because the current is increasing? What will happen because the current is increasing? Think about it. The field which it creates will increase. Remember, this wire will also create its own magnetic field like this. Hold your thumb in the direction of the current. The curled fingers give you the direction of the magnetic field. So, can you see the magnetic field lines are going inside this loop? It will come out from here and go inside. It will come out from here and go inside. From behind, it will go behind like that and come from here. So, definitely, the magnetic field lines are passing inside like this. So, the flux is increasing. The flux is definitely increasing. By Lenz's law, what should you do? You should try to weaken it. So, the induced field should try to weaken the flux. So, to weaken it, you will give an opposite direction field. The induced field should be in the direction opposite to the flux, which is increasing. Hold the thumb towards you. The fingers curl like this. So, hence, the induced current will be in this direction. So, the induced current is anti-clockwise. We got the answer. The induced current is anti-clockwise. So, this is how you solve the questions on, Lenz's law. This is how you solve the questions on Lenz's law. All questions, the process is similar, step by step. Yes, in the rough work, you usually won't write all these things. I'm showing you these steps because that's how you're going to think. And if in the exam you feel that you are getting confused, there is no harm. There is nobody who is going to judge you. Nobody is going to call you inferior if you write these steps in the rough book. Okay, flux increasing. Okay, what did sir say? Flux increasing means it should weaken it. Oh, flux is decreasing. That means it should strengthen it. Where is it decreasing? Here. So you have to strengthen it here. Show the arrow mark, show the direction. I know you can't use these beautiful colors, but if you draw the diagram beautifully, you will do it step by step, systematically. You will not make a mistake. So that's what you are going to do. Okay, perfect. So that was some questions on Lenz's law. Let's start doing some questions on Faraday's law now. Let's start doing some questions on Faraday's law. there is a coil, of, let's say, 10 ohm resistance, through which a flux of 0.5 Weber becomes 2.5 Weber in 0.2 seconds. Question is, find number 1, the induced EMF. Number 2, what is the induced current? Number 3, what is the charge which flows through it? What is the charge which flows through it? Let's try to do this. Okay, let's go step by step. Old and new flux is given, time is given, resistance is given, EMF is asked. If you ask me the induced EMF magnitude wise, it is how much ever the flux changed upon how much ever time was taken. This is always the final minus the initial flux. I'm just interested in the magnitude, because again I'm interested only in the magnitude here. So the induced EMF's magnitude will be final minus initial flux. Final was 2.5 Weber, initial was 0.5 Weber, time taken was 0.2 seconds. 2.5 minus 0.5 is 2 divided by 0.2. So it is just going to be, 0.2, it is just going to be 10 volts. So the magnitude of the induced EMF is 10 volts. Cool. Can we find the current also? Why not? The induced current is always the induced EMF divided by the resistance of the coil. This is Ohm's law. Voltage was 10, coil resistance was also 10. That means the current will be 1 ampere. So an average of 1 ampere is induced within the coil. Can I also find what is the amount of charge which flows? Yes, there was a formula for that. If you remember, it was change in flux upon the resistance of the coil. How much did the flux change? 2.5 minus 0.5. Resistance of the coil, 10. So 2.5 minus 5 is 2 divided by 10. So answer is 0.2 coulombs. So that is the amount of charge which flows in it. Is this absolutely clear, my dear students? Cool. 10 ohms is the resistance. Everything else was given to me. Right. Perfect. Let's go to the next question coming up on your screen. Any doubt till here? Do let me know. All right. EMF using Faraday's law, current using Ohm's law. This we have already seen as a formula over here in the start only. I just gave it to you. The charge flows is change in the flux by the resistance of the coil. This was Ohm's law, this was Faraday's law. Okay, cool. Let's have a look at another question coming up on your screen. A square whose side is basically 0.5 meter having let's say 16 turns has a magnetic field given by 2t square or 2t cube Tesla perpendicular to the coil. Find the EMF induced at t is equal to 10 seconds. Find the EMF which is induced at time is equal to 10 seconds. Let's try to analyze what is given in the particular question. First of all, we have been given that there is a coil. Okay, it's a square of side 1 meter. All right, this is 1 meter. This is also 1 meter. That means the area vector is going to be like this. This is how our area vector will be. Magnetic field is going to be perpendicular to the coil's plane. That means the magnetic field is also in this particular direction only. You don't have to break your head. It is like this. Okay, so this is how the magnetic field is. So the angle between area and the magnetic field vectors are 0. Okay. And it is changing 2t cube Tesla. 2t cube Tesla. Time changes, magnetic field changes. Is deriving the formulas for a question good idea? No. If something is very commonly used, you should remember it. But otherwise, you can derive it. But for that, you should know how to get to that. That means you would have done that problem or model beforehand. Otherwise, don't sit and derive for everything, because you don't get so much time in the mains examination. Let me tell you that. Okay, even for advanced, right? Because you have to be very quick, because the number of marks needed these days is very high for a particular percentile. All right. So in order to do that, first thing I will write down what is the flux probably. The flux is magnetic field into area into cos 0, but there are n number of turns, so I'll multiply it n number of times. Cos 0 is 1, magnetic field is 2t cube, area will be side into side, that means 0.5 multiplied by 0.5, and cos 0 was 1, number of turns was 16. Okay, so I'll get 2t cube, 0.5 is half, 0.5 is also half, and over here 16, 2 cancels, 16 and 2 cancels becomes 8, so it will become 8t cube Weber is the magnetic flux. Now I can find the EMF. EMF is d phi by dt magnitude wise, so you just have to take the derivative of t cube with respect to time. So that will become 8 multiplied by 3t square, which is nothing but 24 t square. That is your induced EMF. But the question says at 10 seconds. So the induced EMF at 10 seconds will be 24 multiplied by 10 square, which is 2400 volts. So that is the answer, the induced EMF at 10 seconds. That's it. No issues, Ritvik. If you have some idea about the chapter, start watching from here. But if you don't, even in the live stream, you can take the cursor behind and start watching it from the beginning. We had a lot of fun, visualizations and animations right from the beginning. All right. So do that. A lot of things which we have seen from the beginning. Okay, cool. So this is how you do this kind of problem where magnetic field was changing. I feel we can also revisit this particular problem, this one, but this time I will ask a slightly different question. I'll ask a slightly different question. Observe this carefully. Instead of asking you what is the induced field's direction, rather I'll tell you, listen, the length of the wire was L, or I can just say the wire was having a square of side A, okay, square of side A. It was turned into a circle in a time of 0.5 seconds. The question is, can you find the magnitude of the induced EMF? Can you find the magnitude of the induced EMF? AC I will teach you probably either next week. Yeah, most likely next week only. NN ideas. Let me complete EMI first. Already your physics portion is going on full speed. I mean, you can't have more speed than this. SHM is done, oscillations is done, waves is done, EM waves is there, nucleus is going to happen, photons, photoelectric effect, atomic structure is done, right, in the last couple of days, weeks. So if you are following the channel regularly, you are getting quality content from top-notch teachers. Let me tell you that. All teachers, obviously very good. Otherwise, I won't even have such teachers on the channel, number one. Number two, you are getting timely delivery, you are getting top-notch content in detail. So it's up to you. Are you going to utilize it? Are you going to tell about this channel to other friends or not? Because if you're not, then you're being just selfish, right? So make sure you let everybody know. Okay. So how do I find the induced EMF? So I need to know the flux before and the flux afterwards. So if you see the area of the square, it will be nothing but a square. But area of the circle is pi r square. I will need the area calculations, but I don't know the radius. So I will do one thing. The length of the wire was always a constant. Length of the wire was always constant. So for the square, the total length will be 4a, a, 4a is the total length. For the circle, it will be 2 pi r. From this, what do you get r as? Check this out, 2 cancels. So 2 times a divided by pi. So instead of r square, just put 4a square by pi square, and then this pi is there as it is. Pi cancels and you will be left with 4a square by pi. That is the area of the circle. Because the area has changed from a square to 4a square by pi, obviously the flux has also changed. So the flux before will be magnetic field into areas, and the flux later on will be again, the flux later on will be magnetic field into area, which is 4a square by pi. This is your magnetic field. This is your magnetic field. So flux has definitely changed. So flux has definitely changed. So because of that, EMF will be generated. So the EMF which is going to be induced is final minus initial upon the time taken. What is final? It is b 4a square by pi. Initial is just ba square. Time taken, it's just 0.5 seconds, which will then give me ba square is common. 0.5 is 1 by 2. Here I will have 4 by pi minus just 1. Yes, okay, perfect. Okay, so 2 goes on the top and I will be left with 2 times ba square, and I'll have 4 minus, I will have 4 minus pi on the top, and below I will just have the number pi. So this is the EMF which is created in this time duration. That's it. I hope this is absolutely clear. Okay, clear everyone? Lo-fi night, it's never about the live watching, it's always about the students who also watch it after the class. So if you see my old classes, maybe, I don't know how many were watching live. It goes to 10, 20, 30, 40,000 also. If you see my 2020 lectures, when we started the channel, hardly anybody knew about the channel, right? Now see the views over there, you know, it has gone, some of the lectures lakhs views. So it's all about students who benefit in the long run. That's why we are here on the channel, or else we would not even keep this recording, right? I would have said only who attend live I will show. I could have been very selfish, but I don't do that. Yep. All right. So moving ahead to the next problem. This is another very interesting question. You will see why. Imagine you have a coil and let's say there is some magnetic field passing through that coil, but this coil is not at rest. Rather, it is found that this coil is made to rotate with some angular velocity. There are some n number of turns in that particular coil. This magnetic field maybe, this particular magnetic field maybe is coming from some magnet placed over here maybe. This is the North Pole and this is the South Pole of some magnet, and this coil is being rotated right now with some angular speed. It is rotated with some angular speed. This coil also has an area of cross section A. What will happen because of that? Sometimes flux will pass nicely, sometimes flux will be less, then less, zero, then more. So flux will change. So definitely there will be EMF which is being created. Can you find the EMF which is going to be induced in this case? The answer is yes. Why not? Let's do that. Let's do that. So just imagine the same problem. I will write it like this. The flux at any instant, the magnetic flux at any instant will be B into A into cos theta, but there are n number of turns, so I'll have to multiply it by n. Magnetic field is B only, area is A only, but I know what I can do with theta. Because it is rotating, using the concept of circular motion, if something turns, if something rotates in some time by an angle theta, the omega is how much angle it rotated per unit time. So theta will be omega t. So theta technically is omega t, and this n will come over here as it is. So I have ban over here. Ban into cos omega t is the magnetic flux through that coil. So using Faraday's law, we can also find the induced EMF. Let me just put it over here. So the induced EMF is nothing but the rate of change of the magnetic flux with respect to time. So the induced EMF with that negative sign, actually it will come like this, if you take Lenz's law also. So it will be minus derivative of this, by the way, B, A and N all are constants. Derivative of cos is basically sine, but with a negative sign. So again one negative sign will come, it will make it plus, and then you have sine omega t. Do not forget omega will also come outside, because sine of or cos of kx's derivative is negative sine kx multiplied by k. Chain rule you have to use. So I basically get, therefore the induced EMF is B A omega n, sine omega t. Very, very interesting result. And out of that, how about calling all these things as E naught, which is your amplitude of the EMF, B A omega n. Sine will keep varying, oscillating between 0, 1, minus 1, 0, 1, minus 1.2. It will keep varying, and this is like the amplitude. And the reason why I may call it as the amplitude is because if I draw the graph of this EMF, which is induced versus time, that graph is going to look like this, a sine graph. This value is going to be E naught, this is going to be minus E naught, this is going to be plus E naught born, and this is minus born. So what is this? One's positive, one's negative, means one's clockwise, one's anti-clockwise. This is nothing but alternating current, AC, alternating current. Very good. This is alternating current, my dear students. In fact, this is the exact principle of working of a AC generator. And Tesla told this many years back. Yes, this is how your AC generator works. Alternating current, born sine omega t. Say for example, I want to design a coil. Which generates around 300 volts. You will see the volts which you get in your houses. The peak voltage, maximum voltage, the amplitude is around 310, 300, 320 volts around. Let's take a rough figure. There is nothing wrong. Okay. And you can say that the area of the coil, a coil which is there, or probably this much, 10 by 10 centimeters, maybe this small coil, zoop, 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 it is rotating. So 10 by 10 means 100 centimeters square. So you can also call it 100 centimeters square coil is there. Okay. And The frequency of our AC is always fixed. The frequency of our AC is already fixed, 50 hertz. Or maybe I want to decide how much area is needed. Let's say how much area is needed. And let's say the number of turns are 10. 10 number of turns are there. So how do you solve this particular question? How do you solve this particular question? 300 volts of amplitude is being generated. So to solve this particular question, just go back over here, this entire thing. The maximum EMF is BA omega n, and this omega is 2 pi f. Let me remind you. This E naught is nothing but 300. Magnetic field also needs to be given to me. So let's say the magnetic field in that region is 10 to the power minus, let's say, 3 Tesla, minus 3 Tesla. So not very strong. Usually magnetic fields are in that region, in that range only, minus 3, minus 2, etc. So you put the magnetic field as 10 to the power negative 3 Tesla. Area I don't know. Omega is 2 pi into frequency. Frequency is 50 hertz. And the number of turns is basically 10. Okay, let's see what happens. Well, you can see few things getting cancelled. 0, 0, 0, 0. Okay, perfect. So I have the number over here 3 is equal to 2 5s are 10. 2 5s are 10, and this minus 3 is there, will become minus 2. So 10 raised to minus 2 multiplied by area. 2 5s are 10 is gone into pi. So therefore the area will be 3 divided by pi. 3 divided by pi into 10 to the power 2 plus 2. It will become 10 to the power plus 2. 3 by pi roughly 1, I can say. So roughly 100 meters square. Roughly 100 meters square should be the area. So it is a very huge coil. 10 by 10 meters, huge. So that much big coil I will need. If I want to reduce the size of the coil, I will increase the turns. Maybe I'll make 1000 turns. Then this will become less area. So that's how the figures are calculated. Why is the frequency fixed? The reason why it is fixed is because all our appliances need to know what frequency should they operate all their circuitry at. If the frequency is different, then the entire electrical characteristics of those devices will change, because there are a lot of components inside, and when you learn AC, you will realize a concept called resonance, and a lot of components like resistor, inductor, capacitor are there inside TVs, fridges, washing machines, chargers, mobile devices, so many things. So if it is not operated at that frequency, then it may not make the device work properly. It might not draw the power or energy, and it might be a complete waste. So that's why frequency is important. Okay. They are real world values. Well, depends from generator to generator. Some person will be like, I have a lot of space, I'll make a big coil. Some person will be like, no, I have very little space, I need an area to be very small. So it depends what size of generators are we talking about. Okay. All right. Okay. Ashwin, I'll let sir know about this, and maybe you can also message me on Telegram. I will definitely look into it. Magnetism and matter mini, just check my old classes on Vedanta JEE English. That's enough because it's a low weighted chapter. Just search for magnetism. Not here, here. Especially on the web browser. On mobile, you don't get this option. So bar magnets, Earth's magnetism is not even there. Use that. Or this is the other chapter. Use this, my Pathfinder lectures. Yeah, use my Pathfinder lectures. It is more than enough. Is that okay? Yeah. And most of magnetism and matter is not there for mains. Yes, Earth's magnetism not there. That magnetic properties, not everything is there. Even the materials also, basic things are there. So just do whatever is required. All right. So you have seen enough examples where magnetic field or area or something or the other is changing, and we are calculating the induced EMF current, their direction, and so much more. Correct. Now, Now, just imagine this particular scenario where you just have a rod or a conductor in motion, Let's say the conductor is maybe moving like this, okay, with some velocity, and just imagine it is touching some wires like this. This is a conducting wire. This is some conducting wire which is touching that rod, and as this conductor moves, maybe in this particular region, maybe there was magnetic field everywhere, maybe say coming towards you or something. Maybe there was magnetic field like this. As you can see over here, the flux which cuts in this particular loop which is formed, this particular flux is definitely changing. The flux changes through this particular loop. And as a result, what should happen if the flux through a coil changes? Obviously, EMF should be created. So definitely there is, the conductor in motion has definitely created induced EMF. It has definitely created induced EMF by Faraday's law. This is as per Faraday's law. Perfect. So this type of phenomena where a conductor in motion which is moving, right, creates changes in the flux and thereby creates induced EMF through Faraday's law. This EMF is sometimes also called as, motional EMF. Motional EMF. Not just this. Here you can see Lenz's law also can be applied. You can find a direction. It's not that difficult. Here the flux is increasing towards you. It's becoming stronger. You will try to weaken it by creating induced field opposite here, because when the rod goes here, more number of lines will come towards you. So to weaken it, you will oppose it by creating a field inside. See how my thumb is pointing inside and the fingers of my right hand are going clockwise direction. So you will naturally notice the current going in this particular direction. This is the direction of the induced current. So motional EMF thereby creating induced current. And the direction can be given by Lenz's law. If by chance there was no wire, only that rod, and imagine it was moving again with that same velocity, in that same magnetic field environment, will there be EMF? Will there be current? Or will there be no EMF? No current. 100% there can't be current, because for a current you need a path, and then there is no path. So when there is no path, there will be no current. But there will be EMF. It's like taking a battery, but the wires are not yet connected. It's not a closed circuit. So you will find EMF, but you will not find current. So this will still behave like a battery, and you will see the battery will be behaving like this. Reason: if this battery were to be connected in this circuit, it will supply the current clockwise. So positivity is here, negative terminal is here where the current enters in, positive terminal the current comes out. So the moving rod behaves like a battery with this particular induced EMF. So this will not have current. There will be no current in this case. There is no current because circuit is not complete. Circuit is basically open in nature. That's why there is no current, but EMF is definitely there. So this part of the rod will probably behave positive, this part will behave negative. That's how it is. Just imagine an imaginary circuit and you will get it. Why is it called motional EMF? Do you see the conductor is in motion? So motional, it is behaving like a battery. Battery has EMFs. So hence a moving conductor in magnetic field behaves like a battery, hence motional EMF. Yep. I'll come to that. Where is it used for? What are the other things? Yes. All right. Yes, you too can generate a current through magnets and coils. Why not? Hi Mini. What are the chapters you are going to teach us? Almost most of the chapters are over. Just probably now only AC is remaining and maybe 1 or 2 chapters here and there. So otherwise, Madan sir will be completing the rest of the syllabus. Everything is done then. Yeah. So you have a complete package. I mean, if after this, if you cry and say that, sir, I did not complete the syllabus, then you cannot blame anybody. I mean, it's like everything was there on YouTube. Also crash course also, and still you did not take advantage, and then you said that I did not complete the syllabus, then the fault lies not within any of us. You have to blame yourself. Yep, correct. Okay, so what is the value of this induced EMF, you might ask? Well, if the length of the conductor is taken L, then the value of this induced EMF is given by this formula. It is length dot producted with magnetic field crossed with the velocity. V cross B. L dot V cross B. Yes, that is what it is. This type of arrangement of vectors, dot with cross, and you are multiplying 3 vectors, 1, 2, 3. So 3 things being multiplied, so it is called triple product. Next, first you are doing cross, then you are doing dot. So when you do cross, it will become a vector. A vector dot producted with a vector, dot product will always give a scalar number. So that is why this entire expression that you see over here, it is called scalar because the outcome is a scalar. 3 things multiplied, so triple, and you are multiplying it. That's why product. Scalar triple product. L dot V cross B. That's all. Yeah. I hope this is absolutely clear. Now I know you might be having a lot of doubts and apprehensions. Sir, how do I use this? Can you teach me that? Because problem to problem things will change. So we'll come to that. Don't worry. But till now, I hope you understood this particular concept of why motional EMF is being used as a separate word. So let us take some examples and we will figure out in each case, is there EMF generated or not? Okay, so basically motional EMF you have to calculate in each and every case. So there is a rod like this, then there is this rod like this, rod like this, rod like this, rod like this, like that, then rod like this. I mean, I've taken all different weird diagrams, all different possibilities which you can probably think of. And in each case, we'll try to figure out what EMF and how much it is. If there are crosses, then it is called as a vector triple product, because once you do a cross product of two vectors, the answer is a vector. Now that vector cross another vector will be another vector. So three things multiplied, so triple product, but the outcome is a vector. So it is called vector triple product. So you have only two things, scalar triple or vector triple, but vector triple is not there here, not needed also for most of the physics. Scalar triple, yes, for this part. Okay, let's start one by one, my dear warriors. First things first, do V cross B. Only, everywhere, always do this first, and then you will get the remaining things. Okay, V is here, magnetic field is inside, velocity cross B is here. So this is the direction of V cross B. Okay, here, velocity is here, magnetic field is towards your right, V cross B, it is going inside the plane of the board. So V cross B is inside the plane of the board. Here, velocity is up, magnetic field is inside, V cross B is going towards the left hand side. So this is where V cross B will be. Here, V and B are opposite, angle is 180, sine 180, 0, anti-parallel vectors, cross product is going to be a big fat 0. So it is not there, it is null vector. Okay, so things are going to be 0 here anyways. Coming to this part, over here, V is here, magnetic field is towards you. So V is right, magnetic field is towards you. I think it goes down. So V cross B is basically downwards. Okay. Here, velocity is towards you, magnetic field is towards the right. I think V cross B goes upwards like this. V cross B basically goes upwards like this. All right. Then we can have one more diagram over here. Last diagram like this, where this is moving like this with some velocity, and then you also have some magnetic field like this. If you do V cross B, again V and B are parallel to each other. So if you do V cross B also, even then you will get 0. It's basically null vector. Now when V cross B is 0, 0 dot anything, 0 into donkey, monkey, whatever, zebra is 0. So doesn't matter. The answer for this, my dear warriors, is a big fat 0. So the EMF induced in this case is 0. Even the EMF induced in this particular case is going to be 0. Is that part clear? Okay. Now observe this. When you do V cross B, whatever that vector is, you are taking the dot product with the length vector. You are taking the dot product of V cross B with the length vector. And when is the dot product a 0? When the vectors are perpendicular, correct? Dot product cos 90, 0. So observe which all places V cross B is perpendicular to the length. Length is here, V cross B is here. V cross B is here, length is here. Oh, it is perpendicular. Can you see that? The length vector is definitely perpendicular to the V cross B. So the dot product will be 0. Yes. So the dot product will be a big fat 0. Hence the EMF induced in this case will also be 0. So a lot of people think there will be EMF induced. No, it is 0 in this case. Let's see over here. I think V cross B is up, length is also in that same direction, so nothing doing. Here V cross B is down, length is at an angle, so maybe there is EMF. Here V cross B is like this. The length vector, the length is like this, perpendicular to V cross B. So obviously V cross B is perpendicular, is basically perpendicular to the length vector. Hence, again, the dot product will be a big fat 0. Hence, the induced EMF is also going to be 0. No induced EMF at all. Now, the only places where there is EMF is probably this, and this. Nothing else. No other places there is induced EMF. Kane, you don't have to watch otherwise. You just watch the crash course classes and finish it off quickly. That's what I would advise you, Kane, if you have watched Pathfinder properly. I would say from the current ROAR series, just download the notes, solve the questions, use it like revision. Just do that. Cool. Now, here length and V cross B is parallel to each other. So cos 0, when length and the vector, when the vectors are parallel, cos of the angle between them, cos 0 will be 1. So hence I will say that the induced EMF will be L into V and B are themselves perpendicular, L into V into B. That's it. L into V into B, because angle between the length vector and V cross V is 0. Cos 0 is 1. Yes, that's the answer. Here, V cross B was like this. Length vector again in this direction. Perfect. You got the answer now. What is the induced EMF going to be? The induced EMF will be LVB. Cos 0 is going to be 1. Same thing over here. Cos 0 is just going to be 1. Here is the problem. It will not be 0. Be careful about it. How will you take the length vector? Will you take it like this or will you take it like this? Understand, always take the length vector because you have two choices. Aligned in the direction of V cross B. V cross B is here, length, take it like that. V cross B is here, take the length vector like that. V cross B is down, show the length vector like this, it will be easier for you to understand. So what is the angle now between them? Maybe there is some angle like this. Maybe that angle over here is theta. So therefore, the induced EMF in this case will be LVB cos theta. Cos theta is this particular angle. Is this clear? Yes. Awesome. Yes, KTG Thermo will also come. Hi Madhva Explorer. Welcome aboard. Awesomeness. Cool guys. Sometimes it is LVB sin theta. Sometimes it is LVB cos theta. Sometimes it is 0. Sometimes it is just LVB. So anything is possible depending on the orientations. So also remember, wherever the V cross B and the length vector I have assumed, that's exactly how the battery will be. So which also means that the positive terminal of the battery will be here. This will be the negative terminal. This will be positive. This will be negative. Everywhere else it is 0. This will be positive. This will be negative terminal of the battery, which is the imaginary battery. Let's take more examples. Okay, as you can see over here, there is an aeroplane which is going from south to the north, And let us also assume some speed. Without that we can't go ahead. So let's say the speed with which it is moving. Let's say the speed with which it is moving. Decent speed, fighter jet, 100 meters per second. Not bad. I mean, it is still lesser than the speed of sound, but most of the jets are even capable of going at supersonic, meaning more than the speed of sound, which is roughly 350 meters per second. Anyway, so 100 is not that great either, so you should not be shocked. All right, now I'm interested, will there be a voltage which is generated across the wingspan? The answer is yeah, definite yes. And we can figure that out, it's not a big deal. So this is a conducting element, because the plane's body is made of a metal, and there is Earth's magnetic field in the complete region. So yes, there is magnetic field in which the conductor is moving, so EMF is generated. So treat this now like a rod. Now treat this like a basic rod like this, which is moving in this direction. So the velocity is here, length is here. Magnetic field, now there are two components, horizontal and vertical. Now this is where many students will make a mistake, so be careful. See, horizontal and vertical. So if you are at any place on Earth, the magnetic field lines go in curved manner and they will hit the surface at different angles. So when it is hitting the Earth at an angle, there are two components. One is the component which is tangential at any place on the Earth, that is horizontal, and the one which is directly normal, which is vertical component. So tangential is horizontal, the perpendicular is the vertical component. Is this understood, my dear students? Is this understood? So think about it. The Earth's magnetic field lines are always in the north to south direction. So the horizontal component of the Earth's field, actually correct. So they'll go like this. This is how the horizontal component of the Earth's magnetic field will be. The vertical component, maybe it is like this. This is the vertical component when you are looking at it from the top down view. This is vertical component. This is up to down. You are looking at it from the top. The plane is going parallel to the ground surface. This is horizontal. South-north direction, the magnetic field will be there. Now tell me, out of these two components, which component can generate the EMF across the conductor? Which component can generate the EMF across the conductor? Think about it carefully. Let's take one by one. Horizontal. If you talk about the horizontal component, I have a feeling when you do V cross the horizontal component, both of them are parallel to each other. So I think the answer will just come out to be a big fat 0, because the angle is 0 and sine 0 degree is 0 only. So V cross horizontal component, parallel vectors, cross product is always 0. What about the vertical? V is here, vertical is down. V cross B inside, the thumb goes towards the left. So clearly over here, this is definitely creating velocity cross vertical component in this direction. Whichever direction V cross B is, take the same direction as the length vector, and obviously this will be the positive terminal, this will be the negative terminal of the EMF generated. That's it. So the EMF which is induced will be L V into B into cos 0, because length and V cross B are in the same direction. So length is how much? 40 meters. Velocity is 100 meters. Magnetic field vertical is 2 into 10 to the power minus 4. Cos 0 is 1. So this will become 4 into 2 is 8. 3 zeros here, 10 to the power 3, and 10 to the power minus 4 here. So that's going to make it 0.8 volts. That's not bad and not something which we can ignore also. Yes, you can write, Anil Kumar, the improvement exam. You should write the improvement exam, or else you will not be eligible. No point taking a drop if you are not cross 75%. Please write it. Is this clear how to solve these kind of questions on motional EMF? Let's do one more question, guys, on motional EMF. Let's do one more question. Imagine there is a capacitor. These are two rails, and on those rails you have a rod which is having a mass of m, length of L, and let's say it is coming down with some speed or whatever. It is coming down with some speed or whatever. Okay, let's try to solve this particular question, my dear students. So I'm interested in what is the charge, what is the current, etc. on that particular capacitor. So if this is coming down velocity wise, and let's say the magnetic field is inside like this, so V is down, magnetic field is inside, V is down, magnetic field is inside, V cross B makes my thumb go towards the right hand side. So V cross B, check this out, is coming out to be towards the right hand side. Just check this out. Take your right hand, velocity is down, magnetic field is inside, the thumb goes towards your right side. Okay. So that means my length vector also has to be chosen in this particular direction. That means this behaves like the positive terminal, this behaves like the negative terminal. Battery supplies that energy. This is negative, this is positive, right? So battery will supply that current. It will supply the current like this. So this is how the current will go. So the current will go like this, like this, like this, and so on and so forth. So this is how the current will go. If current is going like this will be the positive plate of the capacitor. This will be the negative plate of the capacitor because charge is taken away from it. Okay, these are the things which will be there as shown. If you ask me how much is the EMF generated, the induced EMF which is being created, the answer to that will be L into V into B into cos 0, because V cross B and the length vector are parallel to each other. Parallel means cos 0. So it is just L, V, B. So this is the induced EMF. This induced EMF is also the voltage across the capacitor, and voltage across the capacitor, Q is CV, so V is Q by C. So it is Q divided by C. So therefore, I can say Q divided by capacitance is nothing but L into velocity into magnetic field. Now if you want, I can do one more thing. Q is equal to LVBC. Q is equal to LVBC, or I can also write it as LCB, and what is it? Velocity. If I differentiate this, dq by dt, L is a constant, capacitance is a constant, magnetic field is a constant, I will be left with derivative of velocity with respect to time. dq by dt is going to give me the current. dq by dt is going to just give me the current. So rate of flow of charge is current. So this will be LCB into dV by dt, which is nothing but A, which is acceleration, So you can see current and acceleration are related. Yep. I hope this is absolutely clear. How we are progressing. Don't ask me, sir, what are you trying to find? I'm trying to find every possible aspect of the problem. It's Not like you have to limit yourself to only this point, or this point. We will see what and all can we explore in this particular problem. That's the beauty of that. Once I get current is, directly a function of the acceleration, I have something in my mind now that, hey, wait a minute, if there is a current carrying wire, it experiences magnetic force. Oh, I know this. If there is a current carrying conductor, it experiences force. And if this is the current direction, if this is the magnetic field direction, ILB, length cross B goes up. Oh, so there is a force of ILB like this, and there is mg force downwards like this. ILB up, mg down. And a result of both of them is that it is accelerating downwards. So using Newton's laws of motion, mg is down, ILB is up, is nothing but mass times acceleration. Now whether you want to find current or whether you want to find acceleration depends. Let's say I want to find acceleration. I can therefore say mg minus, instead of current, you write it as LCB into A. LCB into A into LB is MA. Therefore, mg is equal to, take this A common, you will have LB plus, here LCB LB. So L square B square C. L square B square and C. Once this minus goes over here, it will become positive. A was anyways common. So from this you will get acceleration is mg divided by LB plus L square B square C. So this is how you can find acceleration, and from acceleration you can again find current. So it depends on what you exactly want to find. Got it, guys? How you can solve problems involving electromagnetism? Beautiful, beautiful question. See, instead of capacitor, you could have even a resistor. Then also the method will be very, very similar. Very, very similar, guys. There is one unique question over here which comes in motional EMF, and that is with regards to rotating rods. So if you have something like a rotating rod, say for example like this is omega, this is L, and then you have the magnetic field like this. Then what is the EMF induced in that? So what you do in such cases is that you break the rod into small segments. You break the rod into small parts, and each part will have a small width, let's say dx, at some distance x over here, and each of this part will have different velocities. A point here will have more velocity, a point here will have even more, a point here will have even less. So the velocities will be different, and in fact the velocity by circular motion is just given by angular speed into x. Angular speed into x, omega into x. Is that right? Omega into x. That's all. If it is suspended by a spring, just Dinesh Yadav, you will just have one spring force minus kx, and you might get some differential equation which you might have to solve. That's all. Yeah, you will just get a differential equation. All right. So coming back over here, each point's velocity is different. So each segment behaves like one teeny mini battery of EMF DE, and there are many such batteries here till here. Many such batteries from here to here. All of them are in series. Hence, I will say that the total EMF which is induced in the rod is the sum of all those small EMFs which you count, because all of them are going to be in series. So EMFs will add, and each small EMF will be that small length which is nothing but your dx into V cross B. Where is velocity cross magnetic field? Magnetic field was inside. V cross B goes towards the left hand side. V cross B goes towards the left hand side. So the EMF will be induced in this direction. So by mistake I assumed it correctly. This will be positive, this will be negative. So this side will be positive, this side will be negative. That means this part of the rod will be positive, this will be negative. So that's what it is going to be. Okay, so dx into angle between dx and V cross B is 0. So cos 0. Dot product is there between length and V cross B. And velocity is V into B as it is. So what will happen next? Well, cos 0 is 1. So this is still dx. This is into 1. Velocity, we just wrote it down over here. It is nothing but omega x, and this is B as it is. Okay. So take constant terms outside, like omega is a constant, B is a constant, only x and dx is remaining. X will start from here till here. So that means 0 to L. Therefore, this will become omega B. X's integration is x square by 2. Limits 0 to L. So it will become B omega L square by 2. That is the EMF induced inside the rod. That's it. Done, dusted. Done and dusted. I hope this is absolutely clear. So you have to remember this as a result. You have to obviously remember this as a result. You cannot spend the precious time in the examination hall for deriving this whole thing. Now you can get some combination questions of rotating rods like this. I have seen some questions like this. See this? There is a rod here, but it is not hinged at the end. Rather, it is hinged somewhere over here, rotating like this. This is L from here to here, and this is 2L from here to here. And this is rotating again inside your magnetic field like this. And the question asked will be, in this, what is the EMF induced across the ends of the rod, across the ends of that particular rod. So what you need to understand first is that you have to divide this particular problem into two parts. Without that, you are doing something wrong. First part of the problem is right side part. The second part is the left side part. Something like this. This is length L. This is length 2L. This is where the particles are going here like this. Here the particles are going down like this because it is on this side of the center. Here it is on the right hand side of the center. Okay. Here the velocities are here. Upwards magnetic field every time is inside. If you do V cross B, it comes towards the left for this guy. V cross B comes towards the left side. If you do it for here, velocity is down, cross with B goes towards your right side. Check that out. So V cross magnetic field goes towards the right side. Why I did this is because I want to know the sign of the terminals. This is the positive, this is negative. Always goes from negative to positive inside the battery. This will be positive, this will be negative. Why I am doing this is because you will see that this is going to act like one EMF, let's say E1, and this is going to act like another EMF, E2, both in opposite directions. This EMF by this formula, B omega length square by 2, B omega length square by 2, length will be 2L, and this E1 will be just B omega L square by 2. Obviously they are not equal, 100%, you can see that they are not going to be equal. And because of that, this EMF will dominate and you will get a resultant EMF in this direction. This is your net EMF, which will be bigger minus smaller. And that net EMF across the ends of the rod, which is E2 minus E1, will be B omega 2L whole square by 2 minus B omega L square by 2, which is 2 square is 4, B omega L square minus B omega L square by 2. 4 minus 1 is 3. So 3B omega L square by 2. That is the final answer. That is the final answer. Is this absolutely clear, my dear students? So it's like two EMFs but opposing, so you have to subtract. So these kind of questions may also come in your JEE examination. Then what other type of questions can come in your motional EMF? This is another common example where you have a region of magnetic field and in this region you know that the magnetic field is inside some region, and then you take a loop which will casually enter inside this, will completely be immersed inside over here, will casually come out from here until it is completely out. This is how the loop is going to move slowly from left hand side to right hand side. And in each situation I'm interested in, what is the EMF which is created inside the loop? Is there any current? What's the direction and all those things? Let's do it step by step. Let's do it step by step. If you look at this diagram and this diagram and this diagram, I'm talking about this diagram labeled A, or let's say P, this is Q, this is R, this is S, this is T. If you look at the diagrams P, R and T, you will see either there is no flux, in them. You can see that there is no flux in them, or there is complete flux in them, but that flux as it moves is constant. Just imagine this guy goes from here to here. What will happen? Nothing. No change in the flux. No change in the flux. So either there is no flux or flux is constant. That means d phi by dt is going to be a big fat 0. So the induced EMF in these diagrams is going to be 0. No EMF at all. There is no EMF at all. Correct? Very good. What about this diagram and this diagram? So the questions can be like, what about these two diagrams? What do you think will happen in, let's say, this diagram labeled, let's say this was P, Q, R, S, T, right? So this is Q, this is R, this is S. What happens in the diagram Q and S? Observe carefully. Observe carefully, guys. Here, as this loop enters inside, more flux will pass through it. So the flux over here is there and is increasing. Flux increases. Whereas here, as this loop goes outside, little bit of area is left. That means the flux through that loop is decreasing. So in the diagram labeled X, flux decreases. And what did we learn in Lenz's law? We learned in Lenz's law that always the change in the flux is opposed. Always the change in the flux is opposed. So induced field will be there. So if flux is increasing inside, induced field will be towards you. Induced field will be towards you. To weaken it. Here the flux is decreasing, so you strengthen it, so the induced field will be basically inside to strengthen it, to strengthen the magnetic field which is going inside. So that's it. Hold your thumb inside, the fingers curl like this, so 100% the current induced is in this direction. You curl the fingers anti-clockwise, the thumb comes towards you, so the current induced is in this direction. So what did you see in this entire diagram? Here, here and here no current, here and here there is current, and the current also is changing the direction. So if you actually ask me how the current will change in this entire scenario, starting from P, Q, R, S, observe this. This is the timeline, this is the current, or this is the EMF. So when you are at P, Q, or even S, there is no current at all. No current, no current, no current at all. But at Q, we got the current to be anti-clockwise. We can take anti-clockwise as positive. There is no harm in that. You can take one as positive, automatically other will become negative. So here it is positive, so automatically other place it will become negative. That's all. So it will abruptly change from 0 to maximum, 0 to minimum. So this is at, oops, P, Q, sorry guys, I wrote Q 2 times, my bad. What did I even do? P, Q, R, and I think labeling went wrong. P, Q, R, S, and this was supposed to be T, I believe. So this was T, this was S, and this was R. This was R. P, Q, R, S, T. Okay. So here also, yes, Q and S, perfect. And here P, R, T. Okay, correct. Perfect. So this is how the current would change with time. This is how the current would change with time. Tell me one thing over here. When the current is anti-clockwise in this scenario, the current is anti-clockwise versus the current is clockwise here, will there be any kind of force which will be experienced by this loop in any of these cases? Will there be any force on the loop in any of these cases? No, the current won't increase if the velocity is constant, because if velocity is constant, EMF is constant. If EMF is constant, resistance is constant, current is constant. So that's the reason why the current won't change linearly, it will be constant, because voltage, EMF, everything is constant. Velocity, and magnetic field and the other things, EMF, will come out to be constant. Okay. So what do you think? Will there be force? Yes. Just consider in the diagram Q and in this diagram S, in this diagram Q and this diagram S, the currents. Current is like this. Here the current is again like this only, like that, like this. Okay, perfect. Only on the part which is inside. Okay, and the magnetic field is like this. ILB, where is the force? The ILB force will be here, length cross B. Yes, ILB force will be here. Here also on this, ILB force will be here. What does this mean? When you're trying to move this rod inside, this ILB force tries to decelerate. It tries to decelerate in both the cases, because we know that the velocity was here. The velocity is opposite to the force. is opposite to the force. So it is trying to decelerate it, but you can't let it decelerate. So what you will do is you will apply another external force to pull it inside. So hence at Q and S, you will have to apply an external force. You will have to apply an external force whose value is ILB to maintain, what do you want to maintain? To maintain the velocity and keep the acceleration 0. That means it has to go uniformly inside. So at this and this place, you have to apply a force, or else it will decelerate, because it is trying to decelerate because of that ILV force. Is this clear? Yeah. Very, very interesting concept. So again, over here, if you see, force is 0, force is 0, force is 0. Only at Q and S you need to apply external force. So external force is needed. External force is needed. Here also external force is needed. Whatever work you do will be used to generate that electricity. Which direction does the force act? ILB force acts towards left side, opposite to the velocity. So external force will be towards the right side to maintain the velocity, as I have shown over here. External force is towards the right side. So it's a very important and interesting question where we discuss the currents, velocities, EMFs, flux changes, everything for every single part of the problem. This is one of the most famous model of the question. Let me tell you that. Now, what happens is, if you take a conductor, and maybe that conductor is in motion, and maybe you are trying to move it between some magnet. So maybe there is some kind of magnetic field. There is some magnetic field as the conductor moves. Because of that, 100% there will be motional EMF which will be set up. Motional EMF which will be set up. But then you will be like, sir, where is the circuit? There is no wire connecting from outside. So where is the current going to be? Agreed. There is no external circuit. But don't forget, the conductor itself has some thickness. Why can't the conductor only imagine itself to be a closed circuit? And imagine there are these current loops which are formed over here. Imagine there is a current loop which is formed right over here. A current loop which is probably going to be formed here like this. Maybe another current loop is formed over here. What if these current loops are formed inside the conductor, which is moving inside a magnetic field? This type of a current is basically called eddy currents. This is called eddy currents. Very, very important thing. Now, because these eddy currents are formed, but we can't know there is current. We will know where there is current. I'll tell you why. Because of these currents, what happens is there is energy loss at the rate of current square multiplied by the resistance of the conductor. Yes, this is in watts. This is in watts. I squared R, heat loss happens. And this energy loss is happening as you move this conductor. So hence, I can say that the kinetic energy of the conductor, goes into heat loss due to eddy currents. This is the concept of eddy currents. This is now useful in many places. Example, I want the kinetic energy to be gone. Imagine there is a car, there is a truck, there is a train, it is moving, and those wheels are made of metals. I bring a magnet close to it. Because the wheel is moving, conductor is moving inside a magnetic field, eddy currents are formed within that wheel, and that currents will create heat loss, I squared R loss, and lot of heat will be generated. Where is this heat coming from? Law of conservation of energy from kinetic energy. So this is used for electromagnetic braking. Electromagnetic braking of vehicles. This concept is also used for, inductive heating and all of that. So electromagnetic braking or inductive heating, all these are based on these concepts. Is this clear, my dear warriors? Yes, that is power. How can you measure it? You can probably keep some water over it. See how much the temperature increases by mc delta T. You can calculate the heat. So different ways of measuring how much heat is generated. So beautiful concept of eddy currents. So I think we have done most of it. Now we have to just do inductors. So let's start with inductors, but after taking a short break. So inductors, we'll take a short break and return. Meanwhile, please like the video and subscribe to the channel if you have not yet subscribed. Okay, so break and return. We'll return in some time. What time? I'll just write it here. Cool. I'll see you guys in some time. Welcome back, welcome back, welcome back. I hope I'm audible, visible to all of you. Quickly let me know in the chat box. Hi Sahil, hi Samir. Kavita, thank you so much for watching me. And good that you're starting your preparation quite early. I'm pretty sure by the time you reach 11th, 12th, you would have probably aced not just the mains preparation, but even the advanced and maybe some Olympiads too. Oh, your name is Loshini and you're in 9th, sorry. Wow. Nice to know you, Loshni. And students who stick to me from 9th standard, I have been telling you again and again. And watching secretly my 11th and 12th standard classes, usually I have seen them by the time they pass out 12th. They are not in any normal college, they are in extraordinary colleges only. So glad to know that. So let's begin with the class. And those of you who have chumma said, yes sir, I have liked, but not yet liked, do that right now. Come on. Where is it? Our video. Go down there and smash that like button on this particular channel. And let me also remind you that the Diwali offer ends tonight. After this, no more sale on any of the courses, books, flashcards, anything. Test series, everything is on offer right now. It ends tonight. After that, the prices increase again. Also, remember that all the PDFs, links, everything are there in the description box as well. I think the Jungle Book, yes, the Jungle Book link is over here. So if you click on the Jungle Book link, okay, you can just register yourself free of cost and you'll get all the PDFs, everything absolutely free of cost. Am I eligible for OBC, NCL, but it takes time to get it, what to do? No, you can fill up, later on you can produce the certificate. You don't need it right now. Okay. Great. This year is my starting. That's a great start, Loshni. All right. So let's start with the topic of inductance. See, what is this inductance and what does it mean? So inductance is basically electrical inertia, that is the tendency to resist changes in current, that is called as inductance. Let me explain this to you with an example. Imagine there is a bulb over here. This is a bulb like this. There is a switch. There is a battery like this and it is connected over here. This circuit is without an inductor. This is without an inductor. Then I will make another circuit, but with an inductor. The same bulb is there. You have this switch over here. You have this battery over here. The inductor is over here. This is the symbol of an inductor, like resistor has this symbol, capacitor has this symbol. Same way the inductor is like the spring-like symbol, that is an inductor. So this is a circuit with inductor. This is a circuit with an inductor. Now, imagine you close the switch. The switch is basically closed. The switch is basically closed and we want to see what the behavior is going to be like. So I will plot the brightness of the bulb. I'll plot how the bulb glows. I'll plot how the bulb glows. Bulb glows with time, with basically time. So starting off, there is nothing, obviously the bulb is not glowing, and then comes the event where you close the switch. You close the switch. The moment you close the switch, in the circuit when there is no inductor, you will see that immediately the brightness will increase within no time, and took, you will see the bulb is on. It will be on instantly. But in the circuit where there is an inductor, there is a tendency to resist any kind of changes in the current. It will not rise, the current will not rise instantly. Rather, you will see the current will rise like this till it reaches a steady value. This is with inductor versus without inductor. Now, imagine somebody decides, okay, now I'm going to open that switch back. I'm going to open it back. I'm going to again open that switch back again. So the moment you decide, at this moment, I'm going to open that particular switch. Open that particular switch. The situation where there is no inductance, instantly the current will drop, and you will see the current will drop and the brightness will become 0, and it continues over here. Instant change. But in the case of inductor, it will resist any changes. It will not allow it to go down so quickly. It will slowly reduce until it becomes 0. This is how the graph will look like. So I hope you understand what an inductor does. It does not allow sudden changes. It will make the changes. It will resist it, for the changes to happen. If the inductance is more or inductance is less, then what will happen? Let's say the inductance is less, then it will rise very quickly and it will also fall very quickly. So the changes are very quick. If inductance is less, that means it does not resist much. And if the inductive property is more, then you will see the changes are very, very slower. You might have seen there are certain lamps, when you turn it off, the brightness does not go instantly. Slowly it will dim. And when you turn it on, zoop, it will not turn on. Slowly it will brighten up. Basically, that's the functioning of an inductor. So there is an inductor behind the scene which you are not seeing, and that is why there is slow changes, subtle, soft changes are there in those bulb functionings. Is this clear? All right, great. Guys, concentrate on the class. Any other doubts, academic, non-academic? That's why I say you should take the personal mentorship. You always have a dedicated person in the batch who is meant to answer all kinds of doubt. Sir, what to do with the certificate? Sir, what to do with the studies? What to do with the timetable? Sir, how to apply for this? All kinds of doubts. There is a dedicated mentor, student academic mentor, your personal teacher, your personal guide meant for you. So check out the link in the description box. You have the Crash Pro Plus, which has that academic mentor and the student guide for all of you. All right? Okay. So now that you understand what electrical inertia, resistance to changes, there are two kinds of inductive properties which can come. Two types of inductive properties which can come. So the first one is where you have a coil, let's say like this. You have a coil and there is some current in it, and let's say that current is producing some kind of magnetic field. This is some magnetic field. Due to the current in that coil, there is some current. There is some current which is flowing inside that particular coil, because of which there is magnetic field. And now just imagine, if that current changes, what will happen? Just think about what will happen. If somebody decides to change the current, imagine the current will change. If the current changes, obviously the magnetic field will change. If the magnetic field will change, the flux inside the coil will also change. And if the flux changes, what happens by Faraday's law? What happens by Faraday and Lenz law? Yes, according to that, there will be an EMF and current. Basically, an EMF is induced. EMF is induced to oppose the change. Because of which it will resist the change in its own current. This property is basically called self-inductance. This is called self-inductance, and how much it is given by the symbol L, and the symbol for that is just a coil like this with the inductance mentioned over here. This is crazy to think of. Imagine I'm studying and then I think of looking outside, look at the kids, they are playing cricket, maybe I should go and play. So there was a change in my attention. Teacher is teaching there, but I'm looking somewhere. But then I remember JEE is just 2-3 months away. I have to get 99.99 percentile. No, I cannot look at them. I have to study. So there was a change which was happening. I mentally self-induced in my mind, no, I cannot, I have to resist that change, and I look back. That is self-induction. Self-induction. In electricity, so if the current tries to increase in that coil, this coil will only say, no, don't increase. If the current tries to reduce, this coil only will say, don't reduce so fast. It will resist. It will eventually do, but it will resist. It will not happen instantly. Yeah. So the magnetic field does not change before the current, it changes because of the current changes, not the other way around. Okay, Nikhil? Hi, Ashwant. Welcome aboard. This is called self-inductance. Now, similarly, I'll come to the formula and etc. in a bit. Hold on. Just imagine there is coil over here. And this coil is placed beside another coil, maybe like this. This coil, there is some current which passes. There is some current which passes over here. Okay. This coil is also called as the primary coil. And in this coil, there is no current, but you can measure the voltages, etc. This is also called as the secondary coil. Now, this primary coil obviously will produce, because of the current, some magnetic field. Some of these magnetic field lines will even enter the secondary coil, as you can see over here. Some, not all, some of them will also enter the secondary coil, as you can see over here. So there is obviously some amount of flux. Oops. Yeah, this was correct only. So obviously there is some amount of flux which enters into the secondary coil. Some amount of flux gets through outside. It does not pass through the secondary coil. Now just imagine there is a change in, somebody changes the change in the primary current. Change in the primary coil's current. What will it do? Obviously, it will change. Its magnetic field being produced. Whatever magnetic field is produced, it will definitely change it. Because the field will change, what will happen because of that? Think about it. Let me create a duplicate. Because of that, what will happen? The flux which enters into the secondary coil, the flux in the flux in the secondary coil will change. The flux in the secondary coil changes. Because of that, what will happen? As per Faraday and Lenz, as per Faraday and Lenz's law, yes, there will be EMF which is induced but in the other coil, in the secondary coil. And this EMF opposes the change, and this property, because it is opposing the change here and this is opposing the change here, it is not in the same coil, opposes the change due to the primary. The secondary is opposing the change due to the primary. This property is then called mutual inductance. Mutual inductance, very, very important. Symbol for that is going to be something like this. You take a coil like this, put one line, and then put another coil over here. This is two inductors together, mutual inductance, mathematical symbol M. Here, self-inductance, the symbol is capital L, just one single coil. So, self-inductance opposes changes in itself, mutual inductance opposes the changes in some other coil. So, it is like I am trying to get deviated. I am trying to change. Somebody else will come and turn my head. Hey, what are you doing? Look here. They are resisting my change. So that is mutual. My friend mutually told me, hey, listen, don't look there. Concentrate on the teacher. You have to concentrate for JEE. That is mutual inductance. By the way, the situation which I have shown over here is very, very simple. Actually, what is happening is much more complex. Let me tell you. Imagine this coil is having changing current. This coil affects this coil and produces electricity. But at the same time, inside this coil, because the current is changing, it will produce an EMF within itself. Not just that, because there is EMF produced here and the EMF could change, there is changing current in the secondary that will create an induced EMF within that secondary, which is self-induction. But because this current is changing, that will have a ripple effect on the primary. That current in the secondary produces its own field which will pass through the primary coil, and that will again create a mutual induction in the primary. That might have again a ripple effect here. So it's going to be crazy. They start, affecting each other. Any change happening here, it is affecting itself, it is affecting this. This change happening, it is affecting this, and it is again affecting this. Because of that change, again it is affecting. It's like, giving it back and forth. Yeah. Eddy currents over. Yes, just it was that concept of how eddy currents are produced and energy is converted into heat. So, my dear students, when we talk about mutual inductance, we are taking into account all the back and forth effects. Remember, every time the effect is propagated back and forth, the ripple effect, it will reduce. So those further ripple effects, just like a decreasing geometric progression, will not have much significance. So when I talk about mutual inductance, it is the net mutually affecting property. It is not just the first time, it is a net mutually affecting property between those coils. That's what we are trying to do. Yeah, like reverse. Okay. Any doubt, yes, I, you have an eddy currents, you can let me know, definitely. Wow, Anime Arcade, you are from MHT batch. Nice to see you over here. All right. So coming back to the formulas present over here for self as well as mutual inductance. Here, the concept is how much flux passes, how much flux passes within that same coil. So I can just say the flux linked in that particular coil is directly proportional to the current in the coil, the current is I, the current is basically I, the flux being created by the field is phi. So phi is equal to L times of I. This is your self inductance. This is your self inductance, and the unit of this is a Henry. You can see current, if taken down, phi by I, phi is expressed in Weber and current is expressed in ampere. So Weber of flux produced by 1 ampere of current is 1 Henry. So if the flux produced is 1 Weber due to 1 ampere, the inductance is 1 Henry. This self-inductance depends on things like, things like the geometry. That means whether it is circular, square, how many turns are there. It depends on the size of it, how big is it, size of it. It also depends on the number of turns and all of that. It also depends on the material present inside. If there is some ferromagnetic material, it will increase the magnetic field. If there is a diamagnetic material, it will decrease the magnetic flux, hence affecting this. So that is what it basically depends on. Not just that, apart from this, you can also see by differentiating this, you can find how much is the self-inductance, which is negative d phi by dt. This negative just says it is opposing, otherwise it is having no meaning magnitude wise. So when I take the derivative of this, obviously inductive property comes outside and I'm just left with di by dt. So the self-induced EMF produced inside a inductor is given by magnitude wise L times di by dt. L times how quickly the current changes. That's all. I hope this is clear. Dropper wale bhi 10th. Yeah, Harish, you have to apply 10th certificate. Yeah. Lunch break. Yeah, surely. We'll have the lunch break after I think around, maybe around 16 hours or so. So let's continue for 16 hours. After that, we'll have lunch break because it is night, no? That's why. All right. Similarly for this, when you look at the flux in the secondary, the flux which is linked in the secondary, that will be proportional to how much current is there in the primary. How much current is there in the primary? The current in the primary, let's say I call it IP. The flux in the secondary, I will let's say call it phi s. This will be equal to, I will put over here the symbol M. This is again mutual inductance, and the unit is again Henry, just like before, 1 Weber per ampere. It again depends on the shape, the size, the material which is present inside. That is what it depends on. So phi is M times of IP. But remember, this is not of the same coil, this is of two different coils. If you again take the derivative of this, you will take the EMF which is induced in the secondary, which is negative d phi in the secondary by dt. So that will be negative. M will come as it is. And I will be just left with the derivative of the primary current. So EMF in the other coil is directly related to the current changes in the primary coil. So two different coils, that's why the term mutual inductance. Some of you will be wondering, sir, if I make this coil primary and this coil secondary, will this M factor remain the same? Answer is yes. So it really doesn't matter who you make primary, who you make secondary. Every time the mutual coefficient is the same. So it really doesn't matter who you are making primary. Keep this in mind. I hope this is absolutely clear. Yeah, very good. Prithvi, I hope this is clear. I don't understand your expressions. How does it not depend on the current of the secondary coil? Why should it depend on the current of the secondary coil? Because when we talk about this flux is produced due to the other coil. Whatever current is there in the secondary and whatever field it will produce, that will be counted as the self-inductance of this coil, not as the mutual inductance of that coil. Mutual is always due to the other, not due to itself. Okay. All right. Sonal, I'm very happy over here, man. You should be also very happy over here. Okay. Right. So let's take some examples to find the mutual inductance and other things and those kind of questions. Let's say trying to find the self-inductance of a solenoid. The self-inductance of a solenoid. Let's try to find that. So say for example, this is our solenoid. Actually, before drawing that, this solenoid will create its own magnetic field which will pass through inside like this. Okay, so this is the length of the solenoid. There is small n, which is number of turns by unit length. This is the total number of turns. This is the turns per unit length, small n. The magnetic field which will be produced inside the solenoid is roughly a constant mu naught Ni, standard result which you should know. Now, just imagine you take any one cross section of that solenoid. In that cross section, there is some magnetic field which is piercing through it, and through every cross section, that means every single turn, the field is passing. So what is the flux through any one such turn? It is field into the area of the cross section. It is field into area of cross section. So if you ask me what is the total flux passing through the solenoid, it will be flux through each turn multiplied by the total number of turns, because every time the flux will intersect n times. So total flux will be one flux multiplied by n number of turns. So this will come out to be B into basically area into number of turns. But B value already I know, it is mu naught Ni, and this area is as it is, this is N over here. But wait a minute, I can do something with maybe capital N or even small n. Small n I can write it as capital N by L, or capital N I can write it as small n into L. Small n into L also I can write it down, because usually small n is given to me. So this is again mu naught Ni. So what will happen now, the total flux through the solenoid, just check this out, is going to be equal to mu naught n into n is n square into L is there, and also area is there, and then multiplied by the current. Check this out, flux is proportional to the current. Where is it? Flux is proportional to the current. Whatever is that constant which depends on geometry, size, turns, materials, etc. is whatever is there in this yellow part. So this must be the self-inductance. Yes, so this must be the constant of proportionality, self-inductance. Hence, the value of the self-inductance of a simple solenoid is permeability into number of turns square into the length into the area of cross section. This is something which it is better you remember it so that you can avoid some time in the exam. Depends on the material. If material changes, mu will change. Number of turns, length, size, shape, everything it has dependent on. Got it, guys? Yeah. Yes, there will be an effect on the primary Divya, definitely. That is always there. One affects two, two affects one. That is mutual. So it is always going to be two ways. All right. Clear, clear, clear. How about doing this question where you have to find the mutual inductance of concentric maybe loops, sometimes concentric even solenoids. The method is the same. Sometimes they will give you two square loops concentric or two circular loops, find their mutual coefficient and all of that. So let's say, for example, this is our primary coil. Inside there is a secondary coil. Inside there is a secondary coil. The magnetic field is produced due to the primary. It will go like this. Not all the fields will pass through secondary, only few of them will. This magnetic field, again just like before, is produced due to the outer coil, which is now called primary. That has a length L, number of turns N1, number of turns per unit length small n1. That means small n1 is capital N1 by length. Okay, the length is the same for both concentric. So N1, which is capital N1 by L, current is I1, area of cross section is A1, and so on and so forth. So all these parameters for the outer coil, primary coil, is given. So this is basically my outer coil. Similarly for my inner coil, which will now be termed secondary, because that's where the EMF will be produced. It has number of turns per unit length small n2, which is capital N2 by L. Current will be generated, some area of cross section is there, and all of that, A2. All right. Now let's calculate how much flux is going in the secondary coil. That means just look at only this much. Only look at that much. So if you see every such cross section of that secondary coil, there are many turns. There are many turns, and through each turn, the magnetic field lines are passing by. N number of times. So the flux through each turn of the secondary coil field into the area, but the area will be of the secondary coil, so A2. This is all secondary turns, B into A2. But let's say I'm interested in the total flux in the complete secondary. So it will be B into A2, but there are n such turns, n number of turns, 1, 2, N2. So N2 will come over here, B, A, N, but A2 and N2. Now let's substitute the value of B. What is the value of B? This magnetic field is produced due to the outer coil. So technically it should be mu naught N1 I1, mu naught Ni of the primary coil, the outer coil. So substitute it over here and let's see what do you get. So the total flux in my secondary coil, will be magnetic field, which is mu naught N1 I1 and A2 N2 over here and A2 N2 over here. But I don't like N2. Instead of N2, I'll write small n2 into L. Small n2 into L. And this is as it is. This is N1, this is I1, and this is nothing but mu naught. I will now rearrange it further. Flux in the secondary coil, observe this very carefully, mu naught N1 N2 into length into area 2, and finally this primary current. Flux in secondary proportional to the primary current. We just saw this. Flux in secondary proportional to the primary current. That constant outside is then obviously mutual inductance. This is going to be mutual inductance. Hence, the mutual inductance of concentric solenoids again depends on material, number of turns, length, size, everything. That is what it is. Again, you can see the formula looks very, very similar to the previous one. Instead of mu naught N square, it is mu naught N1 N2, length into area. Yes, length into area, but the area is of the inner coil. That's the only thing you should keep in mind, not of the outer coil. Yes. Is this clear, everyone? Beautiful concepts, beautiful derivations, beautiful questions. Now, also, sometimes you can have some EMF calculation based questions like this self-inductance EMF or mutual inductance EMF. How will the questions be? Let me tell you that. Imagine a coil current changes from 1 amperes to 3 amperes in 0.4 seconds. The flux linked initially in the other coil is 5 Webers. 5 Webers due to the first coil. Question is, find the induced EMF in the secondary coil. Find the induced EMF in the secondary coil. This is the question. Let's try to do this. Okay, let's try to do this. Well, here, this data is given for a particular reason. Flux linked in the secondary coil is 5 Weber due to the first coil. You know why it is given? The flux linked in the secondary coil due to the current in the first coil. That means mutual inductance has to be found first. So the flux linked is 5 Webers, M not known. Original current was 1 ampere. Therefore, the mutual inductance is 5 Henry. 5 Henry. This is needed. Now we can do the second part of the question. The EMF induced is M times di by dt. What is the mutual inductance? 5. What is the change of the current? 3 minus 1. How much time it took? 0.4 seconds. So 5 into 3 minus 1 is 2 divided by 0.4, which is 10 divided by 0.4, which is 100 divided by 4, shifting the decimals. So it is basically 25 volts. It is nothing but 25 volts. So that's how you can use these formulas. Cool? Great. There is one more thing which I wanted to also tell you over here. There is something called as energy stored inside an inductor. You should know that as well. I'll write it down over here. The energy stored inside an inductor, U inside that inductor is given by half L I square. L is the inductance, I is the current. This is another standard formula which you are supposed to know. Half L I square inductance into current square. And this energy which is stored is in the magnetic form. Very, very important. Very, very important. Half L I square. So maybe we can do some questions on self-inductance also right now. Let's do this. Imagine the question says, current of 4 milliamperes is reversed in an inductor of 10 millihenry. Find the EMF and find the EMF induced and the energy stored later. Find the EMF induced and the energy stored later. And in an inductor, I think one more point has to be mentioned. In an inductor, in 0.2 seconds. The question goes as follows. Find the EMF induced and the energy stored in the inductor. Let's try to do this question. Come on. So first of all, EMF induced can be found by using the formula. The EMF induced inside an inductor itself is what did you say? L di by dt. Inductance already given 10 milli. So 10 into 10 to the power minus 3. Change in the current. Lot of people think it is reversed. Earlier it was 4. Now also it is 4. And the time taken 0.2. 4 minus 4 will be 0. Wrong. This is where many students make a mistake. Something like a ball strikes a wall and the momentum changes. MV minus MV. So direction also matters. So be careful. If the final current is 4, the initial current is not 4, it is negative 4 milliamperes. So 10 to the power minus 3. Many people miss that negative sign. So be careful about it. So 10 into 10 to the power minus 3 is 10 to the power minus 2. 4 plus 4 is basically 8 divided by 0.2 multiplied by 10 to the power minus 3. So this will become 0.2 is 2 by 10. So 10 to the power minus 1, 8 divided by 2. And this is 10 to the power minus 3. 8 by 2 is 4. So this is 0.4 and 10 to the power minus 3 is milli. So millivolt. So induced EMF is 0.4 millivolt. That is the answer. Okay, that part is done. How about finding the energy stored inside the inductor? The energy stored inside the inductor is half L I square. Inductance is 10 milli. So 10 to the power minus 3. Current 4 milli. So 4 into 10 to the power minus 3 whole square. Okay, let's see what happens. This will become half this will become 10 to the power minus 2, 4 square 16, this will become 10 to the power minus 6. 16 by 2 is 8, minus 2 minus 6, that will make it minus 8, I believe, yes. And I can write this as 80 into 10 to the power minus 9, which means this will become 80, this is nano and this is joule. So energy stored is 80 nanojoule. So we got that also. Yeah. Siva, I was born in, yes, Tamil Nadu. Yes, not micro, nanojoules, Siva Prasad. Just see if you made a mistake there. Cool. Let's do another question based on this. My dear warriors. Let's do another question. Come on, let's try this out. It is given to me, there is an inductor with some internal resistance. And it is said for a steady current of 2 amperes, the power loss is, for example, 400 watts. The power loss is basically 400 watts, and the flux linked is basically, you can say, what is that? Flux linked is basically, let's say, 10 Weber. Okay, 10 Weber. The questions are as follows. Find internal resistance of that inductor. Number 2, what is that inductance? How much is that inductance? Number 3, energy which is stored inside that inductor. These are the 3 questions. There is some inductor with some small coil resistance which is called as internal resistance. It's okay. Let's try this out. The current when it is steady, obviously, think about it, if there is current of 2 amperes which is going, there is some heat loss which will occur in this, and that is 400 watts. I think power, resistance, current are related by this formula. P is equal to I squared into R. Power is 400, current is 2, resistance I don't know. Therefore, 400 is equal to 4R. Therefore, resistance is 100 ohms. Oh, so the resistance in that circuit is 100 ohms, which is internal. Cool. Can I find inductance? Maybe I can. Flux linked is given to me, phi is Li. Flux linked is 10 Weber. Inductance don't know. Current 2 amperes. So inductance is basically 5 Henry. Oh, so second part also done. Third part, energy stored in the inductor. U is basically half Li square. Okay, half. Inductance is 5. Current is 2. 2 cancels, 2 5s are 10. So 10 joules of energy is stored in it. 10 joules of energy is basically stored in it. Correct. Awesome. Very good. Very good. Yes, Virat, what is your doubt? I would like to donate to this channel. I mean, the main donation, Arjun, you can do is really by attending the classes and telling this to all your friends, Arjun. Like, Shreyas sir is here. Shreyas sir is doing so much for students from Northeast, South India, abroad, and all the metro cities where students love to learn in English. Okay, because these days everybody studies in English medium and everybody wants to get that international exposure. Everybody knows you will be joining big posts, you will be interacting with big clients in the future when you do job, whatever you do, you start a business, anything. So make sure that this channel is popular. That's the biggest gift. Yeah. All right. Okay. So moving on. So this is also done. This is also done. Yeah, these are the typical questions. One thing you should know, that say for example, you have an inductor. Let's say it is 2 Henry. Example, this is an inductor 2 Henry, and I tell you, listen, here the current is going and the current is increasing at let's say 5 amperes per second increases. Here the current is going like this, but the current is reducing at 5 amperes per second, decreases. And here I tell you the current is 5 amperes constant. What is the difference in all three of them? I'll tell you. Do not forget our equation. The self-inductance EMF is negative L di by dt. Di by dt is given here. This. Okay. L is already mentioned, 2 Henry. If you notice here, current is constant. So technically speaking, over here, di by dt is big fat 0 because this current is a constant. So the self-inductance EMF will be 0. So if there is no EMF across the ends, this just behaves like a simple wire. This just behaves like a wire. When the current is constant, inductor is practically absent. It is as if not there only. But over here, definitely di by dt is not 0. L is 2. Di by dt is 5, which will give me 10 volts. Same thing, L is 2. Di by dt is 5 amperes per second, which will give me 10 volts. This was L. This was di by dt. Now, main thing is, how is this 10 volts going to be written down? Here the current is increasing, inductor will resist it, so it will behave as if there is a battery trying to oppose that. This is 10 volts and the current here is trying to increase. So it will oppose it. So it will behave like a battery in the opposite way. Whereas here in this situation, current is trying to decrease, so it will help it. It will act like this, and this current which was reducing, it will try to increase that current. So that's the difference between these two arrangements when current is increasing versus decreasing. I hope this is absolutely clear. Everybody with me? These kind of questions may come where current is either increasing and decreasing, and you can replace the inductor with an equivalent battery. Very straightforward. Correct. So, say for example, you have been given a circuit like this, where there is an inductor, a resistor like this, and then an inductor, then a resistor, again an inductor over here like this. There is a resistor here, there is a battery here like this. This is E, this is R, this is 2R, this is L, this is 2L, this is 3L, this is 3R. If you ask me, when the current is steady and it is established, how will the current exactly flow? Because the current is constant, so as the current goes from here to here, now the moment it reaches here, it has a choice of either going through this or through this. So what the current does is, it looks at this inductor, and I told you, when the current is constant, it just behaves like a wire. Every inductor will behave like a wire. So wherever you see an inductor, just forget that inductor is even there. And just replace it with a simple wire. That's it. This is the equivalent circuit. Now I know what will current do. Current has two options, either go like this or like this. This is no resistance, this is a resistance, so nothing will go here. All the current will flow from here, zero current. It will again get accumulated here. Resistance, no resistance, obviously no resistance. Here the current will be zero. Again it gets accumulated, comes over here and comes back like this. So this is how the current will flow. In this entire path, like this, when it is going, only one resistance was there. So it is E by R. Current is EMF by R. No other resistance was encountered. That's how the current decides the flow in the presence of an inductor. Correct, Siva Prasad? Awesome. Don't spam, but okay. So I think most of the concepts we have covered, but sometimes you might see that in electromagnetism, they will use this concept of, where did we go? Self-inductance, right? We learned this. Say, for example, whatever inductance we calculated, right? This inductance, if you do this calculation of energy density, this is magnetic energy density, which is the energy per unit volume. Energy per unit volume. Very, very important. Energy per unit volume. Energy was half L I square. And volume is basically area into the length. Don't cancel these two. That length and that is inductance. You can then substitute the value of the inductance, which was mu naught n square L A and all that, which was mu naught n square small l A and all that. Then this current is still there, whole thing divided by 2, and then you also have this area and this length. Area, length cancels, so I think you will be just left with mu naught n square I square by 2. Mu naught n square I square by 2, LA cancels. You can further do one thing. You can write this as mu naught square n square I square by 2 mu naught, and then write this as mu naught ni whole square by 2 mu naught. Notice what this mu naught ni actually is. It is magnetic field. So technically this will just become your energy density, energy per unit volume will become B square by your 2 mu naught. B square by 2 mu naught. This is again a very important formula to calculate magnetic energy density. Obviously the unit of this is joules per meter cube. Joules per meter cube. Just like you had electrical energy density, half epsilon naught electric field square. This is magnetic density of energy. Half 1 by mu naught instead of epsilon naught, and you have magnetic field square. So this formula, you will see the usage of it in electromagnetic waves. A very important formula. I hope this is absolutely clear. Very good. So most of the topics are, I think not most, everything is covered now. Ideally, you should not get combination of inductors, but even if they give you combination of inductors, I'll just tell you the formula and keep, though it will not come, but still. So if you have inductors in series, and this is inductors in parallel. So inductors in series means one after the other inductor. This is L1, this is L2, and so on and so forth. Inductors in parallel means the voltage drop will be the same. The currents will get distributed. This is L1, this is L2. You can combine them into one single inductor. I will call this LS. S stands for series. And this over here LP. P stands for parallel. This LS just behaves like a resistor. So it will be just L1 plus L2 plus L3. And here this behaves just like parallel resistance, not like capacitors. This is 1 by L1 plus 1 by L2. So if at all some need arises, you can combine inductors just like resistors. That's the main thing which you should know. That's the main thing which you should know. Okay, keep this in mind. Inductors in series, inductors in parallel. Very rarely anything will come like that, but still I'm giving it to you. All right. So very nice lecture, I would say, because we have done many questions on inductors also, finding the inductance, defining it properly, eddy currents, different kinds of questions on motional EMF, and defining the flux, finding the change of flux, Faraday's and Lenz's law questions and everything. So if you have loved the way in which I have conducted electromagnetic classes, make sure you say EME-fied, electromagnetism done. So I want this in the comment section. Yes, we have started right from electrostatics, Gauss law, current electricity 2 classes, capacitor separate class, then even equivalent capacitance and resistances separate class, different techniques, magnetic effects of current, magnetic sources of field, and then we started electromagnetic induction today, and obviously EM waves will be taken by Madan sir. Next week we'll have alternating current. Okay, that's what I'm going to do, right? So it's a beautiful series of lectures, and we have covered everything, even mechanics still, rotation done, SHM oscillations, waves also done. So guys, ray optics also taken care of. What more you want? Few more topics left here and there, will be done within no time. Cool. So I want everyone to post this in the comment section. All right. Take care. Have a great time. Thank you for liking. If you have not yet done that, do that. Subscribe to the Vedantu English channel. Yeah, it's very important. And let everybody know about this. Bye bye. Take care. Have a great night.